Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over section 3.3a of our virtual precalculus text on logarithms and exponents. In this particular presentation, we are going to be looking at how to rewrite logarithms as exponents. So the type of problem we'll be attacking in this tutorial is captured in this example here. Rewrite in exponential form the equation log base 9 of 81 equals 2. And we're going to be using this particular property here. Do not forget, we have 10 practice problems at the end of this presentation we'd like you to try out in order to demonstrate mastery of the contents of this tutorial. If this sounds like what you're looking for, don't forget to hit the like and subscribe button. Now let's go ahead and take a look at the formula that will guide our problem solving process. Today's presentation is known as the inverse property of exponents. Let's make this a little bit bigger. Now this is on our website mathgotserved.com/precalc, and we're just looking at the formula collection. We have a lot of formulas here that you can take a look at. All right, so the ones that we're going to be using are the first two, illustrating the inverse relationship between exponents and logs when you compose a exponential function with a logarithmic function. So here you have a raised to the log base a of x is equal to x, and e to the ln of x is equal to x. So what's being illustrated here is that if you have an exponent and if the exponent of that exponent is a logarithm with the same base as the exponent, what you happen is that you're going to have a cancellation action happening. The exponent and the log will cancel out, and you're going to be left with the logarithmic argument. The same applies to the exponential function here, the natural logarithm situation. So we know that the natural logarithm has a base of e, the natural base. So since the base of this exponent is also e, the same cancellation effect happens, and we're left with x. Alright, so the instructions for the examples that we're working on are as follows. We are to rewrite the given logarithmic equations in exponential form. All right, so first one, problem number 1, let's say we have the equation log base 9 of 81 is equal to 2. Okay, all right, let's do this. So the solution is as follows. Log base 9 of 81 is equal to 2. So what you're going to do here is we're going to use the inverse of logarithm to get rid of this log on the left side. Okay, so what is the inverse of logs? Remember, the inverse of logs are exponents. Okay, so which unique exponent are we going to use? Just take a look at the base of your log. The base of the log is 9. So what we're going to do is we are going to exponentiate both sides of the equation using 9 as our basis for exponentiation. All right, so put a big 9 on the left side of the equation and a big 9 on the right side. And then this exponent becomes a little log base 9 of 81 equals 9 to a little 2. Okay, so just take a close look at this. All we did is we used the base of the logarithm on the left to exponentiate both sides of the equation. Okay, so what you had on both sides of the equation initially are now exponents. What does that enable us to do that we couldn't do before? Notice on the left side we have an exponent, and the power of the exponent is a log with the same base as the base of the exponent. That, ladies and gentlemen, is a setup that enables us to use the inverse property of logarithms. These two cancel each other out because they're inverse operations, and you're left with, you bring down the 81, 81 is equal to 9 to the second power. This is the equivalent exponential form of the original logarithmic equation. Okay, let's take a look at number 2. Let's say we have log base 15 of 1 over 225 equals negative 2. So we're going to carry out the same steps, okay? We're going to try and rewrite this in exponential form. So we have log base 15 of 1 over 225 equals negative 2. So we're going to exponentiate both sides of the equation using what? The base of the log is 15. So what are we going to do? Put a big 15 on the left side and the right side of the equation. Bam, bam. And then we're going to exponentiate this equation, all right? So you have a little log base 15 of 1 over 225 equals 15 raised to a little negative 2. They are now powers. On the left side, you have the inverse operation action happening. Those two cancel each other out. And you have the final answer, 1 over 225 is equal to 15 raised to the negative 2. That, ladies and gentlemen, is your equivalent exponential form or equation of the original logarithmic equation. Moving along, let's take a look at number 3. What if we have log base 1 over 16 of 1 over 256 is equal to 2? So let's see right here. We're going to carry out the same set of steps. So we have log base 1 over 16 of 1 over 256 is equal to 2. So do you see what our base is that we're going to use to exponentiate both sides of the equation? Well, it's 1 over 16. We have a fractional base in this case. Alrighty, so we're going to have a big 1 over, let me change colors here. A big 1 over 16 on the left side of the equation and a big 1 over 16 on the right side of the equation. Alright, so we're going to have 1 over 16 and then exponentiate both sides of the equation. A little log base 1 over 16 of 1 over 256 is equal to 1 over 16 raised to a little 2. Okay, so you notice that what we had in the original equation has been exponentiated now like we did in the previous examples. 1 over 16, this exponent has a logarithmic power with the same base as the base of the exponent, so they basically cancel each other out using the inverse property of log. So we have the final answer, 1 over 256 is equal to 1 over 16 raised to the second power. That is the exponential form of the original logarithmic equation. All right, let's take a look at question number 4. So for question 4, what if we have the following equation? Log base 9 of 3 is equal to 1/2. All right, so we want to rewrite this in exponential form. So log base 9 of 3 is equal to 1/2. So we're going to follow the same procedures that we did in the previous examples, okay? The basis of exponentiation is the base of your log. So we're going to put a big 9 on both sides of the equation. And then on the left side, a little log base 9 of 3. And then on the right side, a little 1/2. So both sides of this equation have been exponentiated using 9 as the basis of exponentiation. Alrighty. So on the left side, you see that this exponent and its power, which is also a log, have the same base. All right, so that enables us to apply the inverse property of logarithms that's canceled out. So we have 3 is equal to 9 raised to the 1/2 power. Okay, all right, moving along. Let's take a look at question number 5. Question 5 is a little bit different. Let's say we have log base, no, just say log of 1 of 10,000 is equal to 4. Alrighty, so we are to rewrite this logarithmic equation in exponential form. Let's do it. So log of 10,000 is equal to 4. Okay, now we need to exponentiate both sides of this equation using the base of the log as our basis for exponentiation. So what's the base here? Ladies and gentlemen, if you have log with no base, this is known as your common log. Okay, so this guy right here is your common log. What does that mean? Your common log is log base 10. All right, log base 10. There are two famous logs. We have the natural log, log base e, and the common log, log base 10. All right, because we have the decimal system, that's why it's referred to as a common log. So what does that help tell us about this problem? Ladies and gentlemen, there is an invisible 10 right here. Okay, whenever you have 10 as the base of your logarithm, it's customary not to write it. It goes into the invisible realm. All right, so log base 10 of 10,000 equals 4. Now it's easy to know what we're going to do. We have direction now. We know that the base of our logarithm is 10, so we're going to put big 10s on both sides of the equation, a big 10 here and a big 10 here. And then 10 raised to a little log base 10 of 10,000 equals 10 raised to the 4th power. Little 4. Alrighty? Now on the left side, you're going to see the interaction between these two. This is an exponent, and its power is a log with the same base as the base of the exponent. So we can apply the inverse property of logs, cancel those two out, and we will have to bring down the logarithmic argument. 10,000 is equal to 10 to the 4th power. Ladies and gentlemen, this is the equivalent exponential form of the original logarithmic equation. All right, let's take a look at another one similar to this but slightly different. Number 6. Let's say we have the natural logarithm of 1 is equal to 0. Now, what is the equivalent exponential form for this logarithmic equation? All right, let's do it. So the solution is as follows. We have natural log of 1 is equal to 0. So what is the base of the natural log right here? It's similar to this one. Notice this one has no base and this one doesn't have any base. These are the two logarithms that you do not have to specify the base. But what is the base though? Ladies and gentlemen, when you have natural logarithm, this is called a natural log. So let's write down what the name is. We have the common log and we have the natural log. What is the natural log? The natural log is basically log base e. All right? So the natural log is log base e. So in essence, ladies and gentlemen, we have an invisible e right here. Okay, let's connect that to number 5. Number 5, we had an invisible 10 for the common log. Whenever you have a natural log, you have an invisible e called the natural base. Alrighty? Okay, so now we know exactly how to proceed. We have our basis for exponentiation, which is e. So you put a big E on the left side and a big E on the right side. And then you have on the left side a little ln of e, ln base e of 1, or ln of 1 base e, and then e to a little 0. On the left side of the equation, what do you notice? You have an exponent, and the power of the exponent is a logarithm with base e, the same as the base of the exponents. We can apply the inverse property of logs. Those two cancel out, and we have 1 is equal to e to the 0th power. Ladies and gentlemen, that is the exponential form of the logarithmic equation ln1 equals 0. Okay, let's take a look at question 7. So question 7, let's say we have the logarithmic equation log base root 3 of x is equal to pi. Bam. All right, so let's go ahead and rewrite this in exponential form. Okay, this one looks really, really strange. So log base root 3, you have an irrational base of x is equal to pi. So just follow the same procedure. All right, don't let all these weird symbols confuse you. The base of this log is root 3. So what are we going to do? We're going to put a big root 3 on both sides of the equation. So root 3 on the left and root 3 on the right. And then this gets exponentiated a little log base root 3 of x. And then here you have a little pi as the power. On the left side, root 3 and log base root 3 are inverses, so that's gone, goodbye. And then the final answer, x is equal to root 3 raised to the irrational power pi. That is the exponential form of the original logarithmic equation. Alrighty, let's take a look at question number 8. So for question 8, let's say we have log of y equals 14. Alrighty, let's try this one out. So how are we going to rewrite this in the equivalent exponential form? Let's write the problem log of y equals 14. So let's see here. This is the common log again. So what's the hidden base? For a common log, the hidden base is 10. So put a 10 there. Now we're going to exponentiate both sides of our equation using 10 as the basis. We're going a little bit faster now because you already know how to do this. Bam, bam. Little log base 10 of y and little 14. On the left side, we have inverse operations composed with each other. Gone, left with y equals 10 raised to the 14th power. That's the equivalent exponential form of the original equation. All right, let's take a look at one more. Question number 9. All right, so for question number 9, let's say we have the natural log of z equals 1/3. Let's try this one out. All right, so we want to attack this problem. Then we'll give you some practice problems to try out in order to demonstrate mastery of the contents of this tutorial, okay? Ladies and gentlemen, we have our another celebrity log, our natural log with an invisible base, and we know what the base is. For your natural log, the base is going to be your natural base e. So we're going to exponentiate both sides using the irrational number e as the basis of exponentiation. And then we have the natural log of e, natural log of z base e, or the natural log base e of z, equals e to the 1/3. Bam. On the left side, we can see inverse operations, exponents with a logarithmic power, with the same base as the exponent. So those two cancel each other out. And we have z is equal to e to the 1/3. That's the exponential form of the original logarithmic equation, ln of z equals 1/3. Alrighty, ladies and gentlemen, we have 10 practice problems that we would like you to try out. So go ahead and pause this video presentation at this time. Try out these 10 problems. When you're done, reinitiate playback so that we can be able to show you what the correct answers are for you to check your work. Alrighty, welcome back. Hopefully you had a chance to try the problems. Let's take a look at what the solutions are. For number 1, we have 9 squared equals 81. For number 2, we have 1/13 equals 13 to the negative 1. For number 3, we have 1/1000 equals 1/10 raised to the 3rd power. For number 4, we have 7 equals 49 to the 1/2 power. For number 5, we have 1/9 equals 3 to the negative 2. For number 6, we have 1000 equals 10 to the 3rd power. For number 7, we have 1/e equals e to the negative 1. For number 8, we have x equals y to the negative 19. For number 9, we have x equals 10 to the 13. And then for number 10, we have 3/5 is equal to x to the z power. All right, so those are the answers. Ladies and gentlemen, how well did you do in these 10 practice problems? Let's know your performance in the comment section below. If you have any questions on any of these problems or what we went over in the tutorial, just let us know in the comment section and we'll be more than glad to assist you. Thanks so much for taking the time to watch this presentation. If the contents of this tutorial was helpful in your studies of logarithms, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to subscribe to this channel. We upload math content on a regular basis to our YouTube page. And also to gain access to tons of support resources like the must-know formulas, just visit our website at mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.